The silence before the storm is not peaceful.
It is the held breath of something vast, something ancient, something that has been waiting beneath the surface of the world, gathering its strength in chambers of molten stone, rehearsing in whispers what it will one day scream. On the morning of August 27, 1883, that scream tore across the Indian Ocean with a force so profound that it shattered the very notion of what sound could be. It was heard 3,000 miles away in Mauritius, 4,000 miles distant in Australia. Sailors in the Bay of Bengal thought cannon fire erupted nearby. In the highlands of Ceylon, now Sri Lanka, police officers rushed into the streets, convinced they were under military attack. But there were no armies. No wars of men. Only the earth itself, speaking in a voice that had not been heard in human memory. This is the story of Krakatoa, a volcanic island that became a wound in the ocean. A rupture so violent that it rewrote our understanding of what the planet beneath our feet is capable of. It is a story written in ash and fire, in waves that swallowed entire coastlines in a darkness that fell at noon, and in a sound that circled the globe 7 times, rippling through the atmosphere like the tolling of some planetary bell. It is a reminder that we live not on solid ground, but on a thin crust floating atop an ocean of liquid rock, and sometimes that ocean breaks through. The island was beautiful once. Krakatoa rose from the Sunda Strait, that narrow passage of water between Java and Sumatra, 2 of the Indonesian archipelago's largest islands. It was not one mountain but 3 perbuatan, Danan, and the towering Krakatoa, the latter rising over 2,600 feet above the tropical sea. Dense jungle clung to its slopes. Birds nested in its canopy. The waters around it teemed with life. To the people who lived along the coasts of Java and Sumatra, Krakatoa was a familiar landmark, a navigational reference point for sailors. A distant green silhouette against the horizon, so constant it might have seemed eternal. But eternity is a human conceit. Krakatoa sat atop one of the most volatile geological boundaries on Earth, the meeting place of the Indo-Australian Plate and the Eurasian Plate. Here, in the depths beneath the ocean floor, one vast slab of the planet's crust was being forced beneath another, descending into the furnace of the mantle, melting, transforming, and feeding the reservoirs of magma that would one day demand release. The Earth's restless heart beat strongest here in the Pacific Ring of Fire, where more than 3/4 of the world's volcanoes stand sentinel along the edges of colliding continents. Krakatoa was simply one among many, but it would become the most infamous. The indigenous peoples of the region knew the danger. Javanese legends spoke of Batuwara, a mountain that once stood where the Strait now flowed, destroyed in ancient times by the anger of the gods. Modern geological evidence suggests they were right. There had been a catastrophic eruption here before, around 535 AD, an event that may have altered global climate and contributed to the fall of empires half a world away. But by the 1880s, such legends were dismissed by the colonial powers that controlled these waters. The Dutch East Indies was a jewel in the Netherlands' imperial crown, its plantations producing coffee, sugar, and spices that enriched European tables. The Sunda Strait was a critical shipping lane, connecting the Indian Ocean to the South China Sea, and the administrators in Batavia, modern-day Jakarta, paid little attention to the geological whispers from the island in the middle of the passage. Those whispers, however, were growing louder. May 20th, 1883. The first explosion occurred without preamble. The crew of the German warship Elizabeth, passing through the Sunda Strait, reported a column of ash rising from Perboawatan, the northern cone of Krakatoa. The cloud climbed miles into the sky, a dark tower against the tropical blue, and a sound like distant artillery rolled across the water. The island had awakened. In the weeks that followed, the eruptions continued. Ash fell on the decks of passing ships. Small earthquakes rippled through the strait. Captains reported the smell of sulfur thick in the air, and at night, glowing light pulsed from the summit magma, breaking through to the surface, painting the clouds with hellish reds and oranges. On May 27th, a party of Dutch engineers landed on Krakatoa to investigate. They found the northern peak transformed. Where dense jungle had once grown, a crater now yawned 1,100 meters across and 50 meters deep. Multiple vents spewed steam and ash. The ground trembled beneath their feet. Trees for miles around were coated in gray powder, their leaves stripped away, standing like skeletal sentries in a landscape already half claimed by the underworld. They took measurements, made notes, left the island. Their report concluded that the eruptions, while impressive, posed no significant danger to shipping or to the coastal populations. The vents were releasing pressure, they reasoned. The volcano was simply letting off steam literally. They could not have been more wrong. Throughout June and July, the island continued its performance. Eruptions occurred intermittently, sometimes daily, sometimes with gaps of a week or more. The pattern was irregular, unpredictable. Ash clouds rose and fell. The sound of explosions became almost routine to those living along the strait. Fishermen continued to work the waters. Ships continued to pass. Life went on. But beneath the surface, in the darkness where no human eye could see, something unprecedented was building. The magma chamber beneath Krakatoa was filling. Not gradually, but rapidly, fed by the endless subduction of the oceanic plate below. The pressure was immense, millions of tons of molten rock, superheated gas, and dissolved water, all compressed beneath a cap of solid stone that was growing thinner, weaker, with each passing eruption. The mountain was not releasing pressure. It was loading the cannon. By mid-August, the activity intensified. Explosions became more frequent, more violent. Ash began to fall as far away as Batavia, over 100 miles to the east. The sky took on a peculiar haze. Ships reported pumice floating on the ocean's surface in vast rafts, some pieces large enough to be mistaken for rocks or small islands. On August 25th, the eruptions became continuous. The three peaks of Krakatoa merged into a single roaring column of ash and steam that towered 15 miles into the stratosphere. The sound was deafening for anyone within 50 miles. The ground shook constantly. The sea around the island churned and boiled. Captain T.H. Linman of the ship Loudest made the last detailed observation of Krakatoa before the cataclysm. On the afternoon of August 26th, he sailed within 6 miles of the island and described a scene from the apocalypse. Krakatoa was now one mass of fire. The whole island was burning. The noise was terrific and flames were shooting out at intervals. He did not linger. As night fell, he steered his ship away from the island as quickly as the winds would carry it, racing to reach the open sea before whatever was coming finally arrived. He barely made it. To understand what happened next, to truly comprehend the forces that were about to be unleashed, we must turn from the surface to the depths. We must descend into the earth itself. Krakatoa sits on the Sunda Arc, a chain of volcanic islands stretching from Sumatra to the lesser Sunda Islands. This arc is not random. It is a scar, a seam, where two of the planet's massive tectonic plates meet in violent, slow-motion collision. The Indo-Australian plate, carrying the ocean floor of the Indian Ocean, moves northward at a rate of about 7 centimeters per year. When it encounters the Eurasian plate, which holds the islands of Indonesia and the Asian continent, it does not stop. It cannot stop. The physics of planetary convection, driven by heat from the Earth's core, will not allow it. Instead, it bends. It descends. It dives beneath the Eurasian plate in a process called subduction, one of the most powerful geological processes on Earth. As the oceanic plate plunges into the mantle, the pressure and temperature increase dramatically. At depths of 100 kilometers or more, the minerals in the descending slab begin to break down. Water, locked in the crystal structure of ocean floor sediments and altered basalts, is released. This water rises into the wedge of mantle rock above the subducting plate. And water changes everything. When water infiltrates hot mantle rock, it lowers the rock's melting point. The solid stone begins to melt, transforming into magma molten rock enriched with dissolved gases and volatiles. This magma is less dense than the surrounding solid rock, and so it rises, buoyant, forcing its way upward through fractures and weaknesses in the overlying crust. Eventually, it accumulates in chambers, vast reservoirs of molten stone sitting just a few kilometers beneath the surface. These are not caves filled with liquid rock. They are more like sponges, bodies of partially molten rock mixed with crystals and gas bubbles, held under immense pressure by the weight of the rock above. Krakatoa's magma chamber was one such reservoir, and the magma it contained was particularly dangerous. The chemistry of magma determines its behavior. Krakatoa's magma was what geologists call intermediate to silicic rich in silica, the same compound that makes up glass. High silica magma is viscous, thick, sticky. Gas bubbles cannot escape easily. Pressure builds. When such magma finally erupts, it does not flow gently like the basaltic lavas of Hawaii, it explodes. The magma beneath Krakatoa in August of 1883 was a cocktail of superheated rock and dissolved gases, primarily water vapor, but also carbon dioxide and sulfur dioxide. The pressure in the chamber was staggering, held in check only by the strength of the rock above. And that rock was failing. Each eruption in May, June, and July had fractured the overlying crust a little more. Each explosion had relieved a little pressure, but only a little, because more magma was rising from below, refilling the chamber faster than it could empty. The mountain was not healing. It was breaking. By August 26th, the system was on the verge of total collapse. The magma had risen high enough to interact with seawater, either through fractures in the volcanic cone or through the porous rock beneath the seafloor. When water and magma meet, the result is explosive. The water flashes instantly to steam, expanding in volume by a factor of thousands in a fraction of a second. The explosive force is immense, far greater than the magma alone could produce. This is called a phreatomagmatic eruption, and it is one of the most violent phenomena in volcanology. Krakatoa was now a bomb with two fuses, the rising magma and the infiltrating seawater. Both were converging on the chamber. And when they met, the explosion would be heard around the world. August 27, 1883, 5:30 a.m., the first cataclysmic explosion tore through Krakatoa with a force that defies comprehension. The northern cone, Perboawatan, disintegrated. Millions of tons of rock, ash, and magma were hurled into the sky in a column that reached an altitude of 25 miles well into the stratosphere. The sound was a physical thing. A pressure wave that slammed into the coast of Java and Sumatra, with enough force to shatter windows and crack walls. But this was only the beginning. At 6:44 a.m., a second explosion followed, even more violent than the first. The summit of Denan, the central peak, was blown apart. The eruption column now towered 30 miles high, punching through the troposphere and entering the realm where the air is so thin that meteors burn. Ash and pumice began to rain down across hundreds of miles of ocean. Ships caught in the fallout were pelted with stones the size of fists, their decks buried under inches of gray powder. The eruptions were so powerful that they generated atmospheric pressure waves, literal ripples in the air that radiated outward at the speed of sound. Barometers around the world began to fluctuate wildly as these waves passed, registering changes in pressure even in places where no sound was heard. At 8:20 a.m., the third explosion struck. By now, vast quantities of seawater were flooding into the magma chamber through the growing crater. Each wave of seawater was instantly vaporized, adding explosive fuel to the inferno. The island was tearing itself apart from the inside. And then came the fourth explosion. 10:02 a.m., this was the annihilation. The entire northern half of Krakatoa, a mass of rock, magma, and earth weighing billions of tons, was launched into the atmosphere in an eruption so violent that it ranks among the most powerful explosions in recorded history. The eruption column reached an estimated height of over 80,000 feet. The sound was heard in Perth, Australia, over 1,900 miles away. In Rodriguez Island, near Mauritius, nearly 3,000 miles distant, the chief of police reported hearing what he thought was the distant sound of heavy guns. It was the loudest sound in human history. The pressure wave from this explosion circled the Earth. Not once, not twice, 7 times. Barograph's instruments that measure atmospheric pressure registered the passage of the wave as it rippled outward from Krakatoa, crossing continents and oceans, passing over cities and wilderness, a ghost of sound moving through the air long after the human ear could no longer detect it. The energy released in those 4 explosions has been estimated at 200 megatons, roughly 13,000 times the power of the atomic bomb dropped on Hiroshima. But numbers, no matter how large, struggle to capture the reality of what happened. The mountain did not simply erupt. It ceased to exist. Where Krakatoa had once stood, there was now a submarine caldera, a collapsed crater plunging more than 800 feet below sea level. 2/3 of the island had been obliterated. Rakata, the southern peak, was all that remained. A shattered remnant standing alone above the waves, its northern face sheared away in a vertical cliff that exposed the island's internal structure like a geological autopsy. The explosion had excavated rock from depths of several kilometers. hurling it skyward and outward in a cataclysmic ejection. Pumice and ash covered an area of 300,000 square miles. Ships more than 1,000 miles away reported their decks coated in fine gray powder. But the eruption itself, as terrible as it was not the deadliest consequence of Krakatoa's fury. The true killer came from the sea. The collapse of a volcanic island does not happen quietly. When billions of tons of rock are suddenly removed from above sea level, whether blown apart by explosions or collapsing into an emptied magma chamber, the ocean rushes in to fill the void. The water does not flow gently. It plunges, crashes, converges from all directions at once, colliding in the center with tremendous force. And then it rebounds. The displaced water surges outward in all directions, forming waves that radiate from the source like ripples from a stone dropped into a pond, except these ripples are walls of water traveling at hundreds of miles per hour. Tsunamis. The word comes from Japanese, tsu, harbor, and nami, wave. It is a deceptively calm word for one of the ocean's most devastating phenomena. In the deep ocean, tsunamis are nearly invisible long, low swells that pass beneath ships without notice. But when they approach shallow coastal waters, they transform. The front of the wave slows as it drags against the rising seafloor. The back of the wave, still traveling at full speed in deeper water, catches up. The wave compresses. It rises. What was a 1-meter swell in the open ocean becomes a 5-meter wave in the shallows. Then 10 meters. Then 20. Krakatoa generated not one tsunami but dozens. Each of the 4 major explosions displaced the ocean. The collapse of the northern half of the island created the largest displacement. But even the smaller eruptions and the submarine landslides triggered by the earthquakes sent waves racing toward the coasts. At 10:30 a.m., less than 30 minutes after the 4th and largest explosion, the first wave struck the coastlines of Java and Sumatra. They arrived without warning. The people living in the coastal villages of the Sunda Strait had heard the explosions. Some may have seen the enormous ash columns rising from the island. But few understood what it meant. Few had time to react. The waves came in darkness. The eruption had filled the sky with so much ash that the sun was blotted out. At midday, the region was plunged into a twilight gloom, lit only by the flashes of lightning that rippled through the ash clouds and the eerie orange glow from Krakatoa itself. In that semi-darkness, the ocean withdrew. This is the first sign of a tsunami. The trough of the wave arrives before the crest. The sea pulls back from the shore, exposing hundreds of meters of seafloor coral reefs, stranded fish, the muddy bottom usually hidden beneath fathoms of water. To those who saw it, it must have seemed miraculous, apocalyptic. And then the water returned. The waves that struck the coasts of Java and Sumatra were, in places, over 30 meters tall, nearly 100 feet. Entire villages were obliterated in seconds. Homes built of wood and thatch were swept away like leaves. Stone buildings were smashed apart. Trees were uprooted and turned into battering rams. People were torn from the ground and carried inland by the surging water, tumbling through debris, drowning in the churning mix of seawater, ash, and wreckage. The town of Merak, on the northwestern tip of Java, was completely destroyed. Of its population of nearly 3,000, only a handful survived. The town of Anjar, once a thriving port, was wiped from the map. Survivors who returned days later found nothing but flattened earth and scattered debris. The coastline itself had been reshaped, entire beaches stripped down to bedrock, bays filled with sediment, river mouths choked with the shattered remains of forests. On the Sumatran coast, the village of Telikbatan was struck by a wave estimated at over 40 meters high. A Dutch gunboat, the Beru, anchored in the harbor, was picked up by the wave and carried more than 2 miles inland, deposited in a valley nearly 30 feet above sea level. The ship remained there for decades, a rusting monument to the ocean's power. The waves did not stop at the first coastline. They radiated outward across the Indian Ocean, diminishing in height but still carrying lethal force. Smaller waves struck the coasts of India, Sri Lanka, and the eastern coast of Africa. In some harbors, the sea level fluctuated wildly for days as the waves reverberated back and forth across the enclosed basins. Even as far away as the English Channel and the Panama Canal, tide gauges recorded unusual fluctuations, distant echoes of the catastrophe half a world away. The death toll from the tsunamis alone exceeded 36,000 people. Some estimates place it higher. Entire communities were erased. Thousands of bodies were never recovered, swept out to sea or buried beneath layers of ash and mud. It remains one of the deadliest tsunami events in recorded history. When the sun finally rose on August 28, 1883, the survivors along the coasts of Java and Sumatra emerged into a landscape transformed beyond recognition. The world was gray. Ash covered everything. It lay in drifts several feet deep in some places, smothering the ground like snow. Trees stood as blackened skeletons. Fields that had been green with rice paddies and crops were now buried under layers of pumice and volcanic debris. The air was thick with suspended particles, making it difficult to breathe. The smell of sulfur hung heavy, mixing with the stench of salt, decay, and death. The sea itself had changed color. Pumice floated on the surface in such quantities that ships had difficulty navigating. The water was murky, choked with ash and organic matter. Dead fish floated in vast numbers, killed by the shockwaves or poisoned by the chemicals released from the eruption. Rescue efforts began almost immediately, but they were hampered by the scale of the destruction. Roads were impassable, buried under debris, or washed away by the tsunamis. Communication lines were severed. Many villages were so thoroughly destroyed that rescuers could not even determine where they had once stood. The Dutch colonial government dispatched ships to the region, bringing supplies, medical aid, and personnel to assess the damage. What they found was staggering. Entire stretches of coastline had been depopulated. Survivors, many of them injured, wandered in shock through the ruins. Orphan children were found sitting among the wreckage, too traumatized to speak. The final death toll from the eruption of Krakatoa and the tsunamis it generated is estimated at over 36,000 people, though the true number will never be known. Entire villages disappeared without a trace, their populations lost to the sea. In some regions, the demographic impact lasted for generations. Communities that had existed for centuries were simply gone, their histories erased in a single day. But the impact of Krakatoa was not confined to the Sunda Strait. The eruption had injected an estimated 25 cubic kilometers of rock, ash, and gas into the atmosphere. Much of this material fell back to Earth within hours or days, blanketing the region in a gray shroud. But a significant portion reached the stratosphere, the stable layer of the atmosphere above the weather, where winds blow in great rivers that circle the globe. Here, the finest particles of ash and, crucially, sulfur dioxide remained suspended. The sulfur dioxide reacted with water vapor to form tiny droplets of sulfuric acid, creating an aerosol layer that encircled the Earth. These aerosols reflected sunlight back into space. In the months following the eruption, people around the world began to notice strange phenomena. Sunsets turned brilliant shades of red, orange, and purple, so vivid and unusual that fire brigades in New York and Poughkeepsie were called out, mistaking the glowing sky for distant fires. Artists painted these sunsets. Poets wrote about them. The skies over Europe and North America glowed with colors that had never been seen before. But beauty came with a cost. The aerosol layer reduced the amount of sunlight reaching the Earth's surface. Global temperatures dropped by an average of 1.2 degrees Celsius in the year following the eruption. In some regions, the effects were more severe. Weather patterns shifted. Monsoons failed, crops suffered. The winter of 1883 to 1884 was unusually harsh in many parts of the Northern Hemisphere. Frosts came early. Growing seasons shortened. In places already on the edge of subsistence, the climatic disruption pushed communities into famine. The eruption of Krakatoa did not cause these famines directly, but it contributed to the environmental stress that made them worse. The aerosols remained in the stratosphere for years, gradually settling out or being washed from the sky by rainfall. It took nearly 3 years for the atmosphere to return to its pre-eruption state. By then, Krakatoa had become a household name around the world, a symbol of nature's awesome and terrifying power. Of all the extraordinary aspects of the Krakatoa eruption, perhaps none has captured the imagination more than the sound. The explosion at 10:02 a.m. on August 27th was the loudest sound in recorded history. It was not merely loud in the sense of being uncomfortable or painful to the ear. It was loud in a way that redefined what sound could be. Accounts from ships within 100 miles of Krakatoa described the sound as unbearable. Sailors reported their eardrums bursting. The pressure wave was so intense that it felt like a physical blow not heard, but felt, as a crushing sensation in the chest and a ringing that lasted for days. The sound traveled outward in all directions, weakening with distance but remaining audible for thousands of miles. In Perth, Western Australia, more than 1,900 miles away, residents heard what they described as the sound of distant cannon fire. In Sri Lanka, over 2,000 miles distant, the explosions were mistaken for naval artillery practice. On Rodriguez Island near Mauritius, nearly 3,000 miles from Krakatoa, the chief of police noted in his official report, several times during the night of the 26th-27th, reports were heard coming from the eastward like the distant roar of heavy guns. The sound had crossed the Indian Ocean. But, even where the sound could no longer be heard by human ears, it continued to propagate. The pressure wave from the explosion traveled through the atmosphere at the speed of sound, approximately 1,235 kilometers per hour at sea level. Barographs around the world recorded the passage of this wave, even in places where no audible sound was detected. The wave circled the Earth not once but 7 times. Each time it passed a given location, the barograph needle would spike, recording a sudden change in atmospheric pressure. Scientists tracked these spikes, mapping the wave's journey around the planet. It took roughly 36 hours to complete each circuit, the wave gradually weakening with each passage, but still detectable after more than a week. This global propagation of sound was unprecedented in human history. For the first time, humanity had witnessed and measured a single event whose effects were truly planetary in scale. The eruption of Krakatoa was not just a local disaster. It was a global phenomenon, one that reminded the world of the interconnectedness of the Earth's systems. The island of Krakatoa did not die that day in 1883. It transformed. Where once 3 peaks stood, only a shattered remnant of Krakatoa remained, a lone sentinel rising from the waves. The northern 2/3 of the island had been obliterated, replaced by a submarine caldera that plunged hundreds of feet below sea level. The sea rushed in to fill the void, and for decades, the site of the volcano was marked only by a patch of disturbed water, stained with pumice and warmed by residual heat from the depths below. But beneath the waves, the Earth's furnace still burned. The subduction zone that had created Krakatoa continued its work. The Indo-Australian plate continued its slow, inexorable descent into the mantle. Magma continued to rise. The reservoir beneath the collapsed caldera began to refill. In 1927, 44 years after the cataclysmic eruption, fishermen in the Sunda Strait reported seeing steam rising from the water near the site of the old volcano. Shortly after, a new island emerged from the sea, built by fresh lava erupting from the submerged caldera. The Indonesians named it Anak Krakatau, the child of Krakatoa. Anak Krakatau grew rapidly. Eruption after eruption added layer upon layer of volcanic rock, building the island upward and outward. By the 1950s, it had risen above sea level permanently. By the 1970s, it was over 400 feet tall. By the turn of the millennium, it exceeded 1,000 feet. The child was rebuilding what the parent had destroyed. Scientists watched with fascination and concern. Anak Krakatau was a living laboratory, a chance to observe the birth and growth of a volcano in real time. Seismometers were installed. Satellite imagery tracked changes in the island's shape and size. Geologists made regular visits, taking samples, measuring gas emissions, documenting the evolution of the volcanic cone. What they found was both reassuring and troubling. Anak Krakatau was active, dangerously so. Small eruptions occurred regularly, hurling bombs of molten rock into the air, coating the island in fresh layers of ash and lava. The volcano was building itself rapidly, but it was also unstable. The steep slopes of loose volcanic debris were prone to collapse. On December 22, 2018, that instability led to disaster. A large section of Anak Krakatau's southwestern flank collapsed into the sea during an eruption, triggering a tsunami that struck the coasts of Java and Sumatra without warning. More than 400 people were killed. Hundreds more were injured. Coastal hotels and villages were damaged or destroyed. Once again, Krakatoa had reminded the world of its power. The collapse reduced the height of Anak Krakatau by more than 2/3, from over 1,000 feet to just 300. But it did not end the volcano's activity. Within weeks, new eruptions began, and the island started to rebuild itself once more. The cycle continues. The eruption of Krakatoa in 1883 had effects that extended far beyond the immediate destruction and loss of life. It became a turning point in the history of science, particularly in the fields of volcanology, meteorology, and even telecommunications. Before Krakatoa, volcanoes were understood as local phenomena. Dangerous, yes, capable of destroying nearby towns and altering landscapes, but ultimately limited in their reach. The 1883 eruption shattered that assumption. The global propagation of sound, the worldwide atmospheric pressure waves, the spectacular sunsets observed from Europe to America, all of these demonstrated that a single volcanic event could have planetary consequences. This realization spurred the development of modern volcanology as a scientific discipline. Researchers began to study not just individual volcanoes, but the global distribution of volcanic activity. They mapped the ring of fire, tracing the boundaries of tectonic plates. They developed theories of magma chemistry, eruption dynamics, and the relationship between volcanism and climate. The eruption also provided crucial data for understanding how volcanic aerosols affect the atmosphere. The sulfur dioxide injected into the stratosphere by Krakatoa created a natural experiment in climate modification, demonstrating how particles suspended in the upper atmosphere could reduce global temperatures. This knowledge would later prove critical in understanding other volcanic eruptions, such as Pinatubo in 1991, and in modeling the potential effects of nuclear winter and anthropogenic climate change. Krakatoa also marked a milestone in global communication. The eruption occurred at a time when the world was becoming connected by telegraph cables. News of the disaster was transmitted around the world within hours, a speed unimaginable just a few decades earlier. Newspapers in London, New York, and Sydney reported on the eruption within days, sharing eyewitness accounts, scientific observations, and casualty estimates. But the telegraph cables also transmitted something more immediate: the eruption itself. Submarine cables running through the Sunda Strait were damaged by the tsunamis, and telegraphers at distant stations reported strange disruptions in their equipment around the time of the explosion. Some speculated that the electromagnetic disturbances from the eruption had been transmitted through the Earth itself, though this was never conclusively proven. The eruption inspired scientific inquiry, artistic expression, and public fascination. Books were written. Expeditions were mounted. The Royal Society in London commissioned a comprehensive report on the eruption, published in 1888, which ran to over 400 pages and remains a landmark of scientific literature. Krakatoa became a symbol, a reference point for catastrophe, a reminder of the planet's power, a cautionary tale about the limits of human control. We live today in an age of surveillance, not just of each other, but of the planet itself. Around the world, hundreds of volcanoes are monitored continuously by networks of instruments that measure seismic activity, ground deformation, gas emissions, and thermal output. Satellites orbit overhead, capturing images in visible light, infrared, and radar, detecting changes in the landscape that would be invisible to the human eye. Undersea sensors listen for the acoustic signatures of submarine eruptions. Atmospheric monitoring stations track the dispersion of volcanic ash clouds. This global network of observation is the legacy of disasters like Krakatoa. In the Sunda Strait, Krakatoa is one of the most closely watched volcanoes on Earth. Seismometers buried on nearby islands record every tremor. GPS stations measure the subtle inflation and deflation of the volcanic cone as magma moves beneath the surface. Gas sensors sample the volcanic plumes, detecting changes in the ratio of sulfur dioxide to carbon dioxide that can signal rising magma. When unusual activity is detected, alerts are issued. Hazard zones are defined. Exclusion areas are enforced. The Indonesian government, working with international partners, has developed evacuation plans for the coastal communities of Java and Sumatra. Early warning systems have been installed to detect tsunamis, giving residents precious minutes to move to higher ground. These measures are imperfect. Volcanoes remain unpredictable. Despite all our technology, we cannot say with certainty when the next major eruption will occur, how large it will be, or what secondary hazards it will trigger. Nature does not adhere to schedules or probabilities. But we are better prepared now than in 1883. We understand more, we watch more closely. And when the Earth speaks, we have learned to listen. The lesson of Krakatoa is not that we can prevent disaster. It is that we must respect the forces that shape our world, and that vigilance, constant, careful, scientifically grounded vigilance, is the price of living on an active planet. The Ring of Fire. A planet in motion, Krakatoa is not unique. It is one volcano among hundreds that line the Pacific Ring of Fire, that great arc of volcanic and seismic activity that encircles the Pacific Ocean, from the southern tip of South America through the Andes and Central America along the western coast of North America through the Aleutian Islands. Down through Japan, the Philippines, Indonesia, and into New Zealand, the Ring of Fire marks the boundaries where tectonic plates collide, subduct, and fracture. More than 75% of the world's active volcanoes are located along this ring. More than 90% of the world's earthquakes occur here. It is the most geologically dynamic region on the planet, a zone where the Earth's internal heat is continuously released, where mountains are built and destroyed, where the landscape is in constant, violent flux. Indonesia alone has more than 120 active volcanoes. They are woven continuant to the fabric of life in the archipelago, visible from cities, worshipped in temples, feared and respected by the people who live in their shadows. Some are monitored, some are not. Some erupt frequently with small manageable explosions. Others sleep for centuries, building pressure in silence, waiting for the moment when the crust can no longer hold. Mount Tambora on the island of Sumbawa erupted in 1815 with even greater violence than Krakatoa, ejecting so much material into the atmosphere that it caused the year without a summer in 1816, leading to crop failures and famine across the northern hemisphere. Mount Toba on Sumatra erupted 74,000 years ago in what may have been the largest volcanic event in human history, creating a caldera that is now a lake and potentially driving humanity to the brink of extinction through a volcanic winter that lasted years. These are the extremes, the supervolcanoes, the events that reshape not just landscapes but climates, civilizations, and perhaps even the course of evolution. But smaller eruptions occur all the time. Right now, as you read these words, dozens of volcanoes around the world are actively erupting. Lava flows creep down slopes. Ash plumes rise into the sky. Gas vents hiss and steam. The earth breathes constantly in fire and smoke. We have learned to live with this. We build cities near volcanoes because the soils they produce are fertile. We harness geothermal energy from volcanic heat. We mine the minerals concentrated in volcanic rocks. We even visit volcanoes as tourists, hiking to the rims of craters, standing in awe before the raw power of the planet. But we must never forget that the ground beneath our feet is not as solid as it seems. We live on a thin crust floating atop an ocean of molten rock, and sometimes that ocean breaks through. The reflection. The planet speaks on a clear day in the Sunda Strait. You can see Anak Krakatau rising from the sea. It is a young island, raw and dark, its slopes covered in fresh lava flows and loose scoria. Steam rises from its summit. Small eruptions occur with regularity, puffs of ash, the glow of magma at night, the rumble that rolls across the water. The island is alive, growing, a work in progress. It is beautiful and terrible. Standing on the coast of Java or Sumatra, watching that distant cone, it is impossible not to think of what happened here in 1883. The waves that rose from the sea. The sound that tore across the world. The ash that darkened the sky at noon. The 36,000 lives lost. And it is impossible not to wonder, will it happen again? The answer is not if, but when. Anak Krakatau will erupt again. Perhaps it will be a small eruption, a brief explosion that adds another layer to the growing cone. Perhaps it will be something more. Perhaps the magma chamber will fill and overpressurize. Perhaps the island will collapse again, sending another tsunami toward the coasts. Perhaps in some distant future, the volcano will rebuild itself to the scale of its parent and produce an eruption that rivals or exceeds the 1883 event. We cannot know. We can only watch and wait and prepare. This is the reality of living on Earth, a planet that is not static, not finished, but still in the process of becoming. The forces that created the mountains, the oceans, the atmosphere, and the continents are still at work. They do not care about our cities, our economies, our civilizations. They operate on timescales that dwarf human history, driven by energies that make our most powerful machines seem like toys. But there is something humbling, even ennobling about this knowledge. We are not separate from the planet. We are part of it. We are children of the Earth, shaped by its geology, its climate, its chemistry. The calcium in our bones comes from the shells of ancient sea creatures. The oxygen we breathe was produced by photosynthetic organisms over billions of years. The iron in our blood was forged in the core of a dying star. We are quite literally made of the earth. And when the earth speaks in eruptions, earthquakes, storms, and floods, it is not an attack. It is not punishment. It is simply the planet being what it has always been, a dynamic, evolving, living system. Our task is not to conquer this system, but to understand it. To listen to its signals, to respect its power, to build our societies with the knowledge that we are guests on a planet that was here long before us and will be here long after we are gone. The eruption of Krakatoa in 1883 was a tragedy of immense proportions, but it was also a lesson. A reminder that we are not the masters of this world, no matter how much technology we possess, no matter how high we build our towers or how far we spread our cities. The earth has its own voice, and when it chooses to speak, the whole world listens. In the years since Krakatoa's eruption, we have learned much. We have built instruments to measure the planet's tremors. We have satellites that watch from space. We have computer models that simulate the flow of magma and the dispersion of ash. We have early warning systems and evacuation plans. But we have not tamed the volcano. We never will. And perhaps that is as it should be. For in the shadow of these mountains of fire, we are reminded of something essential. That the world is larger than us, older than us, and more powerful than us. That nature does not exist for our convenience. That the ground beneath our feet is not as solid as we pretend. And that sometimes in the roar of the eruption, in the crash of the wave, in the sound that circles the globe, we hear the true voice of the planet, ancient, indifferent, and utterly terrifyingly beautiful. The explosion the world heard was not just a sound, it was a message. And we are still learning to read it.